Okay. Last time, what did we talk about? That's where we were, and we didn't really chat too much about that. Before that, what did we talk about? Yeah. We talked about extent. And we talked about extent and how we were going to use extent to find K, the equilibrium constant, and Q. What was Q again? Not heat. In this case, big Q. Yeah, the reaction quotient. That can tell you where you are in relation to equilibrium. And then I said we're going to talk about this. This is going to feel somewhat unrelated to what we just talked about, but we're going to use both of these concepts to get to equilibrium. Okay? So we've shown how to calculate Gibbs at standard conditions. What about non-standard conditions? That's where we're just going to have the symbol G. Okay, let's return to the natural variable equation. For G, we have dG. You remember what it's equal to? Yep. Okay. Let's make our lives a little bit easier. If temp is constant, how does this change? Yeah. Because what's 0? Yeah. Okay. If we want to get the change, what would we do to get the change? Yeah, integral, we get a delta. Okay, so we're going to integrate from a standard pressure to the experimental pressure that we're interested in. On integration, standard pressure. What symbol do you think we're going to give that? Yep. And what are we going to give the experimental pressure? Yeah, just P. Make our lives easier. Okay. So we're going to go from P naught to P. For G. Oh, makes this mean dG. Because remember, what does Gibbs depend on? Temperature and pressure. What's remaining constant in this case, at least with our setup? Temperature. So we're going to have G, which is a function of temperature. Yeah, it's the same temperature. And what else would it be a function of? Yep. So we go to our final pressure minus what? It is, but we're gonna be tricky first. We're gonna say this. It's equal to the integral. Now we want that other side, e. Maddie, you are right. This is eventually going to turn into G naught, but I don't want it to be yet because this could be at any temperature right now. Okay. We hit a wall. We can't go any further unless we make some assumptions. What would you assume? If we do that, then pressure would have to be constant because temperature is constant and nothing's changing. Yeah, let's assume ideal gas. Okay, what's our equation of state then? Yep. Manipulate that around. What do we want to solve for? Yeah. Volume, what's volume equal to? Yep, and what are we going to do with that? Yep, plug that right in there. Okay, so now get G at some temperature and some pressure minus G at some temperature and standard conditions pressure is equal to the integral E naught P nRT B dP. Okay, what are we going to do here? Yeah, pull out the nRT, integrate. Yep, integrate 1 over P. What are we going to get there? Yeah. And what's it going to be for our system? Yep. And it's still all equal to this stuff, right? Okay, we're going to do something a little strange. We're going to move this guy over to the other side. So we're left over with G P naught, oops, plus nRT. Okay. You might be asking, why would we push it in that weird form? We're going to see why in a second. It's going to be really beneficial to us to keep our delta G's this way. What are we not changing right now? Yep, not changing temperature. And what else are we not changing? Moles. But we care about a change in composition, right? If we want to consider a change in composition, what do we have to consider? Or when you look back to all the other times we looked at changing compositions, what's another parameter we have to care about? Moles, yeah. Yep. And with those moles, what else do we need? The mu thing, yep, we need chemical potential. Okay. What was mu defined as again? Yeah. Okay, let's look back at this equation. This thing, Maddie, you already gave it away. What is it actually? Yep, this is G naught, right? Or we could say it to be G naught at a specific temperature, because pressure is at P naught. Let's rewrite this in terms of chemical potentials. If we wanted to change these G's into chemical potentials, what would we have to do? Yeah, divide by moles. So that first term is just going to become mu at some temperature and pressure. And what's it equal to? So that changed to a chemical potential when we divide it by N. What does this change into? Yeah, other chemical potential with what symbol? No. Yep. And we don't have to say of a temperature and of a pressure. This is just the standard chemical potential at 1 bar. What about the rest of our expression? Because what do we divide through by? So what's the rest? Yep. Okay. What do we set P naught equal to? Yeah. Then this can just change like that, right? Sometimes we'll use this top one just to be a little more formal. But a lot of times we can just utilize this guy. Okay. You might be saying, how did that actually help us out at all? Let's look at another scenario where we actually try to consider mixing two compounds, two gaseous particles, and let's see if we can calculate the change in Gibbs. Do people at least feel comfortable with the mathematics to get to that point? Okay, we'll see the benefit of expressing our G's that way in a second. So question. What is delta G of mixing? So if we want to consider mixing two particles together or two compounds together, we have this mix as a subscript. And we're not going to be very creative. We're going to say A and B. At a constant temperature. Everybody feel like they know what they are doing right now? Ish. How are we going to find the Gibbs of mixing? Delta, it's always what minus what? Yep. Okay, let's define each of these terms. And we're going to do it based upon utilizing this guy. Okay, G of I. We looked at partial molar volumes and looked at like a change in partial molar volumes in the past, but we've also done it with the Gibbs energy. If I want to do this framed upon with moles of A, what do I got to multiply moles of A by to get the change in Gibbs? Yep, I got to multiply by mu of A at whatever conditions we have, right? And then what about for B? Yeah. Okay. We have another way to express each of those mu's. We just determined it down here. Let's sub that into our equation. So we get n sub A times what? Yep, mu naught A plus yep, and what conditions are we going to have? P sub what? A and yep. Plus, what else do we got? Yeah. Same thing for B. So we're starting at some initial pressure, we're going to some final pressure. What's the expression for G sub F going to look like? Yeah, same thing, but with final pressures. Okay. So N sub A, oops, times mu of A, mu naught of A, RT ln PA F plus N B B RT ln right? Okay, this is where I typically, there's a lot going on. I might write a symbol incorrectly. If you spot it, call it out, okay? What do we got to do next? Subtract them from one another, right? Ugh. Okay, final minus initial. RT ln oops. Do we have enough space? I think we do. Oh. So I have a guy at my house building a shed right now. And I thought he was coming next week. Came this week. I had to level a spot. So I started digging at 6 in the morning to like level a spot. Oh my God, my hands are so tense. I'm not used to manual labor anymore. Working with chalk's really hard. Okay. This might be the longest expression we've had so far in class. What do you notice? Can anything go away? Mm-hmm. Yep. So these mu naught terms, all of them gone. And you say distribute through. We could do that in a second. What else could you want to distribute just to clean it up a little bit? Okay. The RTs won't cancel, but we could pull them out. Let's put all the A terms and the B terms near one another. EAF. Oops. What are we going to subtract off this guy? Yep. Plus, what do we get for the other term? Yep. Okay, what can we do with this? Yep. Using the property of logs, we can do division. Stack them. Yeah, stack them's fine too. I would go with that. Actually, I like the term stack them more than divide them. I don't know why. Right? Because we're just subtracting through. We'll stack them. I feel like I have ticks everywhere. We'll get that as an expression. Okay. We still really haven't talked about the mixing part. We can make this even more simple if we consider what we're actually doing. So let's draw a little picture. What color do you want A? What color do you want B? Red and green? Ugh. Christmas. It's horrible. Walmart's already playing Christmas music. It's like, just wait. That's awesome. That's like playing like What's Up Pussycat over and over again. I usually go into a bar, and before I leave, I throw in like $10 and just wham, smell you later, nerds. Have fun with that. Okay. I forget which one was A and which one was B. Okay. Why, does the What's Up Pussycat thing happen too? That's fantastic. Because no one can be mad about that. And if you are, you're unpatriotic. Okay, so we're pretending that we have a partition where these two things are not mixing with one another. And we open it up. And what's going to happen? They mix, right? It's never like A just sits in its corner and B sits in its corner, assuming there isn't big density changes. Have you guys ever seen sulfur hexafluoride or videos associated with sulfur hexafluoride? Sulfur hexafluoride is way more dense. If you flood it into a fish tank and you build a little tinfoil boat, you can actually float the little tinfoil boat. So, because the sulfur hexafluoride is really deep, you can inhale it. I'd suggest to check it out online. When I used to do this with students, I'd pick I'd pick a girl who had the highest pitch voice, and she comes out sounding like it's hilarious. The problem becomes is it's really dense and it just sits in your lungs. So I did that once and I almost passed out because you have to be able to do a handstand to get it all out of your lungs. And I thought I did my handstand long enough and I didn't. So half of my lungs were full of this stuff. And all of a sudden I was writing. I'm like, I think I need to lie down. And then I lied down. So Dr. B doesn't let me do that one right now. But assuming that there really isn't big density changes, sorry, flinging chalk. If we let it sit long enough, what will happen? Yeah, they'll mix evenly. So we'll have A and B all throughout here, right? Okay, let's say we started with this point. We had it like together. We can pretend we had an initial state where they were separated because they're state functions, right? We can actually set our initial state to kind of wherever we want. All right. So now, what could we do with our initial pressure? What could we say, looking at this picture, where's our initial state? Here, right? Oh, I should have written in red. And then our final state is somewhere in here, right? What could we say our initial state is here? Does it have to be mixed with B? No. What could we say it is? Sorry, what was that? We could just say that this initial pressure is the pressure of whatever species we're looking at that time. So if we had this, we could just say it's the pressure of pure A by itself. And what did you say, Shannon, about their pressures? Yeah, they should be the same at the end, or at least they'll reach a point of equilibrium. So what we're going to say is that. After they mix. So we're going to change our expression a little bit. RT ln P star over P, oops, we need this of A, plus NB RT we're going to pull in some Gen Chem knowledge. See if you remember it. Let's remember Raoult's law. Okay. It had to deal with partial pressures. So we're going to say our final pressure of some species I is equal to the initial pressure of I, pure I, and we got to multiply it by something. What's that thing? Yeah. Mole fraction of I. What's that P? Yep, the initial pressure, that's of pure I. And this thing, the star, what is it again? Yeah, pressure of I in mixture. That was a deep sigh, Maddie. That's okay. I feel the same way right now. Oh, God, what's coming up? I don't like this term. What could we do with it? Or does this look pretty close to that? What would you suggest to do? Yeah. Okay. So what's chi sub I equal to? Yep. So now what we can do is we can sub that in. Okay. Why might this equation be more favorable than this guy? So comparing these two. Moles are easy, most of the time, right? Here, you just have to know moles. You're good to go. Here, what do you have to know? Yeah, four different pressures and the moles of your species. So it might be more beneficial to utilize that guy. Okay. Now this is where we know species A and species B, right? We haven't said anything about if they're behaving ideally or not. If these are ideal gases, the moles of A and the moles of B, are they really different if they're both ideal? Not really. Because what do you know about ideal gases? How much space do they occupy? Yeah, supposedly none. What about their mass then? Yeah, exactly. So you could reframe this in terms of total moles. If you have an ideal gas. Oops. Where N total is the total number of moles but I don't want to waste the time deriving it. You guys are going to have a daily problem where you have to utilize these and to know when to utilize them. Okay? A Quizlet question on the very last one will probably be related that way. Okay. Let's talk about the entropy of mixing and one other thing, and then we'll be done for the day. Am I okay to erase this stuff? You feel like you could take, well, you might need to take this one and transform it into this one. To do that, what's N total equal to for our system? Yep. So you can use that fact and transform it into that guy. Okay? Any questions? Yes, Serena?
Wait, why is N total pi A equal to NA?
Oh, okay. So, I don't like that one. There you go. Chi A, what's it equal to, or how do you calculate a mole fraction for A? What goes up top? Yep, moles of A, and what goes in the bottom? Yep, total moles, or Na plus Nb, because we only have those two. N total. Right? Any other questions?